Hi everyone. This video will cover the standard procedure of finding a transition state by using the quantum chemical method. So for today, the molecule that we are going to look into is a simple conjugated diene. So let's make a new molecule. I'm going to start with a carbon atom. Alright, so this diene has two minima in energy. One of the minimum lies in the trans configuration, as what you see on the screen, and the other one, you have to rotate the dihedral angle between the 4 carbon atoms Now this is a cis configuration, and this represents the other minimum in energy for this diene molecule. Now in reality, this diene may flip from one configuration to the other, so from the cis to the trans and vice versa, but in order to do so, it has to climb the activation barrier that separates these two configurations. Somewhere between the trans and the cis configuration is what we call the transition state, and the Gibbs free energy is the largest at the transition state. In order to find the transition state, first we have to guess how it may look like. So if we take a look at the dihedral angle again, make sure that we have rotate groups on both sides so that the CH2 groups move together as a unit. So for the cis configuration, the dihedral angle is 0 degrees, and for the trans configuration, the dihedral angle is 180 degrees. So we're going to guess that the transition state lies somewhere at right angle, so about minus 90 degrees. So let's click OK. So it looks a bit like that. This is 90 degrees. You view it from this way. If you view it from this side, it'll be very obvious that it has a 90 degrees angle. So once we have this, we are going to run the job. So as usual, press either Ctrl G, or we're going to do a calculate Gaussian calculation setup. They both do the same thing. So first we'll go to job type. There are a few options on the drop-down menu under job type, and to get the transition state, you have to run an optimization. However, it's often a good idea to also do a frequency calculation at the same time, because you'd want to check if what you have is really a transition state by checking the vibrational modes of this molecule. We'll talk a little bit more about this later. So, as we see here, we normally do a optimization to a minimum if we would like to find the optimized geometry of the molecule. But in this case, because we are looking for transition state, we are going to choose TS Bernoulli, that stands for transition state. And we are going to calculate the force constants just once. This will be calculated at the end of the job. And we are not going to compute Raman. And next, for the method, if you're doing an experiment, you would know what method you'd like to use and which basis set to use. So for now, I'm just going to make use of a semi-empirical method. This is going to be a very fast calculation, so hopefully that works in our favor. And next, what I'd like to show you is this link 0 tab. So this controls the PC. For example, the memory limit can be set to whatever we want. If you know what is the RAM capacity of the PC, it'll be even more useful. But for small calculations such as this, we probably wouldn't need so much of memory, somewhere around hundreds of megabytes or 1 gigabyte. That should be fine, right? So the next thing is this shared processors. So nowadays, computers come in dual or quad core. To check number of processors that your current PC may have, what you do is you press Ctrl Alt Delete, and then we'll go to Task Manager, and under Performance, you should be able to see the number of cores and the number of logical processors. Now I work with Windows 8. If you guys are using a different version of Windows, this tab may look a little bit different, but you should be able to still see the number of cores. There are only 2 processor cores in this PC. It appears as 4 logical processors due to what we call hyper-threading. But for the purposes of Gaussian, we have to use number of cores, number of real cores that is actually contained within the PC. So we should not be specifying any number greater than this number. So in this case, I'm going to specify 2 cores for this PC. All right. So for this calculation, we are going to perform this calculation in vacuum, which means that this molecule is not going to be surrounded by other solvent molecules. However, it is perfectly possible to run a computation of the solvated molecule. All you need to do is go to the solvation tab, change the model to, let's say, default, and then you can change the solvent to water, DMSO, or any other solvent that you'd like to use. For now, we are going to leave it as a calculation that is done in vacuum. So we are going to keep the solvation model to none. So once we are done with this, we are going to submit. Alright, so now the calculation is running. You just have to wait patiently for it to end. It should not take a very long time. And once it's done, we will view the log file. To do that, let's open the log file. So we'll change this to log, and we are going to tick this for this time. So what happens is that you see this 1 of 7. Now what happens after we tick the option just now is that the intermediate geometries are now available for us to visualize. So this is a starting geometry, 1 out of 7, and we can see how the optimization works. So at 7 out of 7, this is the final geometry. So if we check the dihedral angle, well, it's close to 90 degrees. Here it actually says 91.0357 degrees. So that is pretty close to right angle. And according to Gaussian, this is the transition state between the cis and the trans configurations of the die-in. Another thing that you might find useful is that you can view the results. So here we see that the job takes only 1 second. You could read the single point energy over here and all the other useful informations. So what we are going to do next is that we're going to open the checkpoint file. This contains a little bit more information than the log file. It has the normal modes of vibration also recorded inside. So we can take a look at them by going to Results, Vibrations. So here's the IR spectrum, and if we look at the frequencies, you could animate the molecule to show which bonds are being stretched. There are also bending frequencies that happen at lower frequency than the stretch frequencies. And then finally, we have what we call the reaction coordinate. If we were to look from this point of view, we can see that this is the motion of the molecule when it transits from the cis configuration to the trans configuration. And as you can see, from this table, the frequency appears to be negative when all the other frequencies are positive. So what's going on here? In a normal mode vibration, the molecule is at a minimum in energy when all its bond lengths, angles, and dihedrals are at equilibrium. Any deviations in these parameters will cause the potential energy to go up, so the molecule will vibrate along this what we call normal mode, just like the CH stretch that you see on the top right corner of the screen. When you try to calculate the frequency, since E increases at both sides of the curve, the vibration frequency is calculated to be a real number. But select the transition state mode and the molecule is at a maximum in energy. In this case, any deviation in the bond dihedral causes the energy to go down instead. Gauss shows an oscillation, but in reality, a molecule will never oscillate this way. Instead, during the transition state event, it will reach the peak in energy, coming from the reactant side and slides down the potential energy gradient into the product side. When you try to calculate the frequency, you are forced to take the square root of a negative number because the energy is negative. And you arrive with an imaginary number. The frequency is imaginary. Caution: unable to show complex numbers, instead report this as a negative frequency. Finally, in order to determine the activation barrier, you will need to compute the Gibbs free energy of the molecule at the transition state and again at the initial state. To do this, simply open the log file that you have generated earlier and we will look for free energies. And there you have it. This is the Gibbs free energy of the molecule at its transition state. You can copy this down to Excel, run another job to compute the Gibbs free energy of the initial state and subtract the two to get the activation barrier. This concludes the video tutorial on how to find a transition state by using the quantum chemical method. Hope you have found this video helpful and thank you for watching.